Hey everybody, it's Miss Berry. In this video, we're going to go over sections 5.1 and 5.2, which are about discovering functions. So we'll talk about the language of functions, and then we'll talk about linear growth. All right, so let's go ahead and get started. All right, so the language of functions. In this section, we're just going to talk about some basics of functions. We'll talk about what a function is. We'll talk about how you notate functions, independent, dependent variables, all kinds of stuff, just really basics of functions. So the first thing we need to talk about is what is a function? So a function is a mathematical equation that describes a relationship between two variables. All right, and those two variables are known as, those two variables are known as the independent and dependent variables. But before I talk a little bit more in depth about independent and dependent variables, I wanted to talk just really quickly about function notation. So function, trying to write small, function notation. So functions are special. They're sort of like special equations. And since they are special, they have special properties. They follow special guidelines. And so we need some way to show that we are dealing with a function, and sort of just some way to differentiate it from a normal equation or a normal relation. So we use function notation to do that. This is what function notation looks like. We use f, and then we have this little parentheses, and inside the set of parentheses is the variable x. So f of x is just a fancy way of writing y. So it's just a fancy way of writing y when you're dealing with a function. And let me just explain what all these letters mean. F is the name of the function. X is the, x and y are variables. That's what I wanted to write. Let me erase that. X and y are our variables. Now you can use any letters here. You don't have to use F for the name of the function. You could use G, you could use T, it doesn't matter. Sometimes you may be dealing with a function, you want to call it something that's maybe related to the function. So for example, if you're dealing with the height, you might want to name your function H for the height. X and Y, again, are the variables. These can be any letters as well. But traditionally, we use the letters X and Y. All right, so let's talk about independent and dependent variables. So you can see here, X is what we would call our independent variable, also known as the input variable. So the independent variable, also known as the input variable, that's the number that you're plugging in. So the independent variable is going to be the number or the expression that you're plugging in. The dependent variable here would be y. That's the output variable. So that is the output. That's the number or the expression that you're getting out. The independent variable, or the value of the independent variable, does not rely on the values of the other variables in the equation. But the dependent variable is different. The value of the dependent variable depends on the value of your independent variable. It depends on the value of the input. So that's why they call it the dependent variable, because its value depends on the other variable. So let's look at a couple of examples that will prepare us for some of the homework questions. So I'm going to fill this in. This will be number 1. We'll say find f of 2, or actually let's do 5. F of 5 for f of x equals 2x minus 5. Then down here we'll put find f of negative 3 for f of x equals x squared plus 2x plus 3. So this is kind of like part A and part B. Part A, part B. All right, so what we're doing here is called evaluating functions. Evaluating functions is just a fancy way of saying plugging in numbers into functions. That's all we're going to be doing here is just plugging numbers into functions. So it says find f of 5. Again, that's read as, so this is read as f of 5. Find f of 5 for f of x equals 2x minus 5. So everywhere there's an x, we're going to replace that with 5. So everywhere there's an x, we're plugging in 5. So that's going to be 2 times 5 minus 5. So 2 times 5 minus 5. You can see when I plug in this number, I like to put it in a little parentheses. I think it looks neat that way. There's no way of getting confused and thinking that, you know, sometimes if you write it like this, you might get confused and think that's a decimal. So there's no confusion about what's happening there. You know you're multiplying. So let's plug this in. Let me pull up my document camera. Here we go. All right, so clear out what you got in there. Let me see if I can, well, I think it looks better this way. We'll just do like that. All right, so plugging in 5. So we have 2 times 5, close parentheses, minus 5 is 5. Now that one was an easy one. We could have done that one in our head. Let me make that a little bit smaller, sorry. So there's our answer. Again, this was our output. 5 was our output here. It just so happened that 5 was also our input. It was just a coincidence. Your input doesn't have to match your output. So we plugged in 5 and we got out 5. Now let's do the second piece. Part B. Find f of negative 3 for f of x equals x squared plus 2x plus 3. All right, so f of negative 3. Again, I'm going to put this in parentheses. Negative 3 squared plus 2 times negative 3 plus 3. It's very important that you have the negative 3 in parentheses here when you're squaring it. That's going to tell your calculator, okay, you're doing negative 3 times negative 3 here. So very important that you do negative 3 in parentheses. All right, so let's plug that in the calculator. Negative 3 squared plus 2 times negative 3. Notice that I'm using the negative sign and not the minus. Plus 3 is 6. Okay. That's our output this time. Our output was 6. Our input was negative 3. Look what happens if I don't put this in parentheses. So if I just do negative 3 squared plus 2 times negative 3 plus 3 gives me the wrong answer. It's not because of this piece here, the 2 with the multiplication symbol negative 3, that's fine. It's here in the beginning. Your calculator thinks what it's supposed to do is square 3 and then make it negative. So it thinks it's supposed to do 3 squared is 9, make that negative. So that's -9. So just make sure you put that negative number in parentheses anytime you're raising it to a power. Okay. Let's look at our next example. This is straight off of the homework. It says complete the table by evaluating the function f of x equals -2x minus 6 all squared for the given values of x. So it gives us this little table, and it's already got some stuff filled in. You can see it's missing these 3 boxes right here. So we need to fill those in. All right. So we're going to plug in -3 into our function. So I'm going to go over here to my calculator and start plugging this in. I have parentheses, -2. Then I'm going to put a little -3 in parentheses because that's what I'm plugging in. All right, and then I'm back over here. -6 close parentheses squared. That's 0. And that one's filled in, that one's 4. Now we're plugging in -1. All right, so parentheses, -2, put a little -1 in parentheses because that's what we're multiplying by. -6, close parentheses, squared is 16. And then plugging in 0. So parentheses, -2 times 0, times 0, -6, close parentheses, squared is 36. So if you have one of these multi-line calculators like I do, let me show you what you could have done instead. Let me go down here and clear everything. Let's say that I just typed this first piece in. All right, so that was the first thing I did. Instead of retyping all this, let me show you what you can do. You just use this up arrow right here. Highlight what you just plugged in, hit enter. Then you can kind of just use your little arrow button here to go through and change that number. We wanted to plug in a -1 next. So that's 16. Then you could go up here, hit enter again. Use your left arrow button to go over, type in 0. Now we got an extra number, so you can just hit this delete button. So see, that makes it a little bit easier. You don't have to retype everything each time. So if you do have a TI-36X Pro or any multi-line calculator, you can do that. All right, so our table's filled in. Filling in a table or completing the table is a good skill to have whenever you go to graph functions. So make sure you know how to do that, how to fill in a table. All right, next we have this problem here. It says graph the given equation by evaluating integer values of x from -2 to 2 and then plotting the resulting points. All right, so let me see if I got a little graph on here somewhere. I don't. Let me go get a coordinate plane real quick. We're just going to go to Google and get one. I always use the same one, this one right here. All right, so we'll just put this on here for when we go to graph this in a minute. We actually might just put that on the next page. All right, that's better. Sorry, guys, I should have done that before I started. Okay. Graph the given equation by evaluating integer values of x from -2 to 2 and then plotting the points. All right, so here we have y equals -2x plus 5. I'm going to make a little table. So I'm going to, let me use this little line button on here. I can never draw a straight line on this writing tablet. That's straight-ish. Okay. So I'm going to make a little table of x and y values. It tells me to use the x values from -2 to 2, the integers from -2 to 2. So that's the ones I picked, -2, -1, 0, 1, 2. And now I'm just going to plug those in. So -2 times replacing x with -2. All right, so that's +4 plus 5 would be 9. We're making little ordered pairs here, so that's really what we're doing. We're making little ordered pairs. This first one is -2, 9. All right, so let's plug in the next one. -2, plug it into our equation here. -2 times -1 plus 5. So that would be +2 plus 5 is 7. Plug it in 0. -2 times 0 is 0. Plus 5 would be 5. Notice how it's going back down by 2 each time. You could use that pattern to fill it in if you wanted to. So it's -2 times 1 is -2 plus 5. That would be 3. -2 times 2 would be -4. -4 plus 5 would be 1. All right, so let's write down our little coordinate pairs. We have -2, 9, -1, 7, -1, 7, 0, 5, 1, 3, and 2, 1. Just write them down real quick on a piece of paper for when I get to the graph on the next page, so I don't have to flip back and forth. Okay. All right, so now let's plot these points. I forgot to number this one. This one was number 3. Sorry about that. That's number 3. So now let's plot these points, and then we'll graph our line. So -2, 9. So to the left 2, and then down 9. I know this is 10, so this must be 9. -1, 7. So that's 9, 8, 7. 0, 5. So 0, 7, 6, 5. 1, 3, 3. Oh my gosh, I'm going on the wrong. I'm doing the negative side. I'm sorry, you guys. No one's here to stop me. Let me start over. Sorry, I was going -2, -9. Let me start over. Okay. -2, +9. So to the left 2 and up 9. To the left 1 and up 7. 0, 5. 1, 3. And 2, 1. There we go. I'm going to use my little line tool here to draw my line. Still missed one of them. There we go. It's a little bit better. All right, so you just connect them with a line and then you're done. Make sure you put an arrow on both ends. There's my equation. All right. So now that we've talked about graphing, let's talk about domain and range. Anytime you talk about functions, we typically will mention the range. Whoops, I must have unplugged something. Here it comes again. I must have unplugged it again. Sorry, you guys, I'm having some technical difficulties over here. So anytime we talk about functions, we typically talk about the domain and the range. The domain of a function is the set of all inputs of a function. So in layman's terms, this is all the numbers you're allowed to plug in, or all the numbers that it makes sense to plug in. So all the numbers you're allowed to plug into the function. The range is similar. It's the set of all outputs of a function, or all the numbers you're allowed to get out. Or all the values that it makes sense to get out. All right, so let's look at the example from the homework that involves the domain. There's no examples that involve the range on the homework. All right, so this is, I think, number 4. Let me check. Yeah, this is number 4. It says you belong to a gym where the base membership is $36 a month, and then each group fitness class you take costs an additional $3.25 per class. Write a function in X that represents the total amount that you spend on your gym membership in a month. And then the last part says, be sure to indicate any domain restrictions. All right, so here's our function. We'll just call it f of x. You could call it like C for cost. So off the bat, even if we take no classes, we have to pay $36 a month. All right, so right off the bat, we got to pay the gym $36 a month. And then in addition to that, so we're going to do plus. In addition to that, we're going to pay $3.25 for every class we take. So we'll do $3.25 times X, where X is the number, X is the number of classes taken in a month. Okay, so this is our first part of our answer up here. So 36 plus 325x, that's our function. Now we need to think about domain restrictions. Okay, so remember the domain is the input values. Here we're plugging in the variable x. So we're thinking about restrictions on x. All right, so x again is the number of classes you could take in a month. So let's think about how many classes you could take in a month. You could take 0 classes. You could take 1 class. We wouldn't include numbers like a half a class or 1.5 classes, because even if you left in the middle of a class, they're still going to charge you for the whole class. So numbers like 0, 1, 2, those would make sense to be plugging in, and so on. So we would say that x has to be greater than or equal to 0. So that's our restriction on x. For some reason I can't see my cursor. There we go. So this is our restriction on x, or restriction on our domain, is that x has to be a number that's greater than or equal to 0. All right. The last example I wanted to do just involves reading a graph. This is number 5. It says, if the population is 6,000 people, what is the time in years according to the given graph? All right, so before we answer the question, let's just look at this graph. It's time versus population. We got time down here on our horizontal axis, or our x-axis. Population's on our vertical axis, or our y-axis. When we read a graph, we read it just like how we would read a sentence. So we start on the left and move towards the right. So here, what's happening to this function as we start on the left and we move towards the right? What would you say is happening? It's decreasing, right? So this function is decreasing. Now they didn't ask us about that. I'm just telling you how to read a graph. So this one is decreasing. So sometimes this can be confusing for people because they see this up arrow and they think, oh, okay, up means increasing. But this just means that as you move to the left, it's going up. But if we read graphs the way we're supposed to, which is left to right, we can see that it's decreasing. All right, so let's look at when the population is 6,000 people. So here's population, here's 6. So go over to the graph, then go down to the time. So you can see the time was 1 year. All right. So that's everything for section 5.1. We're going to move on and talk about section 5.2, which is called linear growth. All right, so now we're going to be talking about specific types of functions for the rest of chapter 5. The first type of function that we talk about, the most basic type of function, is a linear function. So let's talk about what a linear function is. Linear functions have the form f of x equals ax plus b, where a and b are real numbers. So graphically, linear functions appear as lines. So graphically, they are lines. And these lines can look one of 3 ways. They may be increasing or rising from left to right. They may be decreasing or falling from left to right. Or they could be constant, so they could be straight across. So whether or not these lines are increasing, decreasing, or constant depends on the slope of the line. So let's talk about the slope of a line. The slope of a line, the first way you learn slope is probably as rise over run. Rise over run is really just a simplified way to say the change in y over the change in x. So it's how much y is changing. It's either going up or down. That's the rise, divided by how much x is changing. So it's either going left or right. It's the run. Now, slope has a specific formula. We won't have to use it in this section, but just in case you need it for future reference, this is the slope formula. It says the slope of a line passing through the points x1, y1 and x2, y2 is. All right, so here's the slope formula. It's m equal little m. We always use little m to define the slope. So it's y2 minus y1 over x2 minus x1. So that's the slope formula. Like I said, I don't think we'll need it in this section, but just in case, that's it. All right, and the last thing I need to tell you before we move on and do an example is I need to give you a definition for slope-intercept form of a linear equation. So slope-intercept form looks like this. It's y equals mx plus b, where m represents the slope and b represents the y-intercept. And typically we will write the y-intercept as a coordinate pair, so you'll see it written as 0, b. The y-intercept is where the graph crosses the y-axis. So if we're on the y-axis, our x value must be 0, and b is our y value, our y-intercept. All right, so let's do an example. This will be number 1. We'll do part A and part B. So it says, find the slope and the y-intercept of the following linear equations. Express the y-intercept as a coordinate pair. All right, so to figure out what the slope and the y-intercept is, the easiest way to do that is to put it in slope-intercept form, which is y equals mx plus b. So y needs to be by itself. So that's what we're going to do here in this first one. We're going to get y by itself. So we would subtract 10x from both sides. Then divide everything by 6. All right, so just cancel this stuff out. That cancels, that cancels. So we get y equals -1/6 minus 10/6. That reduces to, see, 2 goes into both of those. So that would be 5/3 x. I like to write my x off to the side, but you can put it up there in the numerator if you want to. And then just to make it match up with slope-intercept form, I'm going to write the -5/3x first, then minus 1/6. It does not matter, though. You haven't changed anything by doing that. All right, so now let's identify the slope and the y-intercept. All right, so the slope is the number attached to x, so that's -5/3, -5/3. And the y-intercept, it says to write it as a coordinate pair. So that's going to be 0, b. Here, b is -1/6. All right, this one's a little bit easier because you can see y is already by itself. All right, so again, the slope m is the number that's attached to x, so that's -1/5. And notice there's no y-intercept indicated here, so we know there's like a +0 out there. So we'll write y-intercept is 0, b. Here, b is 0. So 0, 0 is the origin. Okay. The last two problems are word problems. We'll start off with an easy one and do one that's a little bit harder. It says the water depth of a pond is initially 30 inches and it decreases at a rate of 0.1 inches per day through evaporation. What will the depth of the pond be after 10 days? All right, so right now it's at 30 inches. It's decreasing. So we know that our final answer should be something less than 30. All right, so it's going down at 0.1 inches per day for 10 days. So 0.1 times 10 is 1. Let me just show you. 0.1 times 10 is 1. That's 1. So that means it went down 1 inch over the 10 days. So 30 inches minus 1 is 29 inches. So that's the depth of the pond after 10 days. All right, and then let's look at the last one. Number 3. It says you can purchase a car for $17,340, or you can lease it for $310 a month with a down payment of $600. How long can you lease the car before the amount of the lease is more than the cost of the car? All right, so very important sentence or very important part right here at the end. How long until the lease is more than the cost of the car? So that's really what they're asking us. They're wanting us to find out how long until the lease is greater than what we'll call the purchase price. All right, so when you lease a car, you never own it. You have to give it back to the dealership at the end of the lease. And of course, if you purchase the car, it will, if you finance it, it will belong to the bank, whoever you financed it with, until you pay it off, and then it will belong to you. You'll be able to receive the title for it. So let's see. We already know the purchase price is $17,340, so that's going to be the right-hand side. But we don't have a formula for the lease yet, so we got to make that. So the lease is going to be, we got to pay $600 up front. That's our down payment. That's a one-time fee. And then we're going to pay $310 per month. So we'll say 310 times X, where X is the number of months. All right, so now let's go in here and we will replace our lease with our formula for the lease. Then we will replace the purchase price with 17,340. All right, so let's plug those in. We have 600 plus 310x greater than 17,340. All right, so we're going to solve for x here. So we're just going to move this 600 over. So we get 310x greater than, that's 16,740. Then divide both sides by 310. That gives us x is greater than, let's plug that in, 16,740 over 310 is 54. So after 54 months, you might as well have just bought the car. All right, so that's our answer. The answer is 54 months. So that means after 54 months, if you're still leasing that car, you've paid more than the purchase price. So you might as well have just bought the car. Now, typically something like this wouldn't happen because if you're leasing a car, it's typically something short term, like maybe a couple of years. So 54 months is pushing it. Like you might have a lease that's like 24 months. And then you take it back to the dealership and maybe you go get a new car and you lease that one. But for the purposes of this problem, we would say that after 54 months, you might as well just purchase the car. All right, so that's everything for sections 5.1 and 5.2. If you have any questions over, the language of functions or linear growth, linear functions, just let me know. Otherwise, I'll see you guys soon.